Hello everybody. Just to get started, let's go over what one-to-one and onto mean. Okay, so these are the two things that we started right after your last exam. So, what what on earth does something being one-to-one mean? So, does anybody have? I mean, obviously you guys are at different stages of knowing this stuff. So one-to-one, the basics that you need to think about it is one-to-one means you have most way at most one way to get to every b. Okay, so if you have at most one way, that means you either have one solution or no solution. Okay, so the implications with that are all kinds of different things. If you only have one way to get there, that means you have no free variables. I'm going to write this stuff down as we go. It means you have no free variables. It means if you have no free variables, it means the dimension of your null space is 0. It means just all kinds of stuff. It means you have a pivot in every column. Okay, so one-to-one, that's how you find it, but at most one solution, this little upside down A means for all B. Okay, what else does that mean? It means we have no free variables. That's not how you write a B. Free variables means you have a pivot in all columns. So these are like the big, like basic ideas behind it. So there's a bunch of different, like I'm sure in one of your, actually I know in your slides it has like it's like characterization of one-to-one. This is what like the technical definition is. This means this one-to-one. It also means this, and this. So if we have a pivot in every column, that also means all columns are linearly independent. And that means your dimension of your column space of A is equal to number of number of columns, means your dimension of your null space equals 0. Okay, these all mean exactly the same thing. Okay, if it says, hey, for this particular matrix, we have no free variables, is it one-to-one? Yeah, that's the definition of what that means. Okay, are there any questions about what makes something one-to-one?
I just had a question. Like,
Hmm?
column space is basically the number of pivots, right?
Say that again.
Column space, like the column space of A.
Hmm.
That's
You can think
basically
of
just
column
a
space as, yeah, you can think of column space as like your span, as we were doing in the first few weeks. That's like by definition what that is. The column space of A is the span of the vectors within the matrix A. Yeah, so the span of the linearly independent vectors, because the dependent ones don't contribute anything, so they're not really necessary. And then the null space, I'll write those definitions, and I guess I probably should have started with those. Column space of A is equal to the span of A. That's the easiest way to think about it. The span of the columns of A. Appropriately named column space. And then we also have the null space. Okay? And the null space deals with our solution set. Okay? Null space is the solution set of AX equals 0. Okay? So the solution set, how do you find that? You get to row reduced form, put it in parametric form, and your parametric vectors are the like whatever, I'll get like x2, call it like v, call it v2, plus x3, 3. This is just like a general showing parametric form. So null A in this case would be the span of v2, v3. Okay, that's just the basic definition. That is the definition of null space and column space. Okay, they're the things that we've been doing for the whole semester, just named a little bit differently. Okay. Okay, so that covers one-to-one, and now we're going to talk about onto, and then we'll get into some problems. Well, then I'll do some matrix multiplication, and then we'll get into some problems. Okay, onto, as you might imagine, it is different than one-to-one. They are not mutually exclusive, though. You can have something that has both. Okay. So onto means you have at least one solution. How did I format this? One solution for all B. Okay. So that means there's like, this also means range equals codomain.
I have a quick question.
Uh-huh.
What is the difference between just saying the column space of A and the dimension of the column space?
Yeah, so the column space of A, it's like, or the span of all of those. Like the column space creates like a plane or like an R3 or a line or a point or something like that. The dimension is how many vectors make it up, okay? Or how many linearly independent vectors. So for example, if the column space of A creates like an R4, the dimension of it is 4 because it creates a 4 space. If that's a little bit roundabout saying it, but does that answer your question?
Yes, thank you.
Okay.
Kind
Um,
of, branching off of that, sort of.
mhm.
You said the column A is the span of the A,
Yeah.
and you said null A is also the span of the columns. Like, what's the difference in that?
Yeah, so
Isn't that what V2 and V3 are?
these V2 and V3 are independent of our A. These are like, we get like a row reduced echelon form, something like this. Okay, and then from here we get our parametric form.
I see. And those vectors, the answer is the span of those.
Sorry, someone can mute themselves. They're typing very loud. Yeah, so like this would be our null space for like whatever, like say this, we get A, and then this is RF of A, and then we get this. So our null space is the span of these two vectors.
Okay.
Okay. And from this reduced row echelon form here, we would take, to find our column space going backwards, we would take this column, and they would give us our column space. So in this case, like the dimension of the column space, we have two linearly independent vectors. It's 2. We have these two linearly independent vectors. In this case, our null space dimension is the same. 2 vectors once again. Okay, so the dimension of the column space is 2, dimension of the null space is 2. Dimension of the column space, you can also think of that as your number of pivots. And dimension of null space, you can think of it as your number of free variables, okay? Or your number of not pivot columns. So, like, the rank nullity theorem states dimension of your nullity plus dimension of your column space equals the number of columns, which hopefully should be pretty intuitive after thinking about your column space is your number of pivots, or your dimension of your column space is your number of pivots, and your dimension of null space is your not pivots. So you add up your number of pivots and not pivots, and that should give you every column, because every column is either one of those two. Would those also be basis? Yeah, that would create a basis of R2 in this case for the column space. Yeah. Okay. Going back to onto, are there any more questions about those two things? Again, these are just like general conceptual stuff to lay the groundwork, and then we're going to go through some questions and stuff. I said in the announcement that we will go to 7:30. I can stay a little later. It might go to 8 or something along those lines. So, okay. Any questions?
A quick question. So
Mhm.
one of the questions on the quiz was about a vector being in the column space,
Mhm.
and it wasn't a pivot column, but it was still chosen.
Mhm.
It was question 4 on I think
Okay.
this one.
Just to talk generally, I'm not going to go ahead and look at like questions and everything, just so we can get this stuff
Okay.
squared away first. Not to like brush you aside or anything like that. So the way that one works is like, so given like, let's say this is our like A that we got this from. Okay. In this case, the row reduced echelon form of A would be equal to A. But like this and this would define our column space because they would range all of R2. But this is still in that column space, right? It's linearly dependent upon these. I believe that's what that question is. So hopefully that answers that.
Yeah, no, that makes sense. Thank you.
Absolutely. Range is the span of the columns and codomain is where the vectors live. That is correct. But yeah, that is correct. That's the definition of range. It's the span of the columns, and the codomain is where those vectors live. We'll come back to that. I'm sure there'll be questions about codomain and range and all of that stuff. So I'll define that after this. So onto means you have at least one solution. That means your column space. Well, no, that doesn't tell us anything. Sorry, I don't want to say the wrong thing. Where is this pretty place? Okay. Columns of A. M is your rows,
Right,
right?
this is a little bit referring to the last part you were writing about when you were talking about one-to-one. When you wrote the upside down A symbol next to the B,
It means for all.
For all, okay, thank you.
Yeah. So for all B, for every B inside the codomain, for every like vector B we can find. Yeah, just some math notation. Professors like to just write it and assume that you guys know it. Sorry about that, but I'm just very used to just making it a little bit simpler. Okay, so onto at least one solution. This means we can have some free variables. This is just telling us that onto means for all of your x's, you can get all of your b's. That's like the whole point of onto. For one-to-one, that means for every like x, you have a unique b. Okay, that's the whole like big overarching idea. That's what it means by at most one solution. You can only have one way to get there, or you can have no way to get there. That doesn't mean that like because something is one-to-one, it creates all of our like we can get all b, but it means every b either has a solution. It doesn't mean there are solutions. And for onto, it means like we're taking where we were and we're getting every b. Okay. There's different applications of this. Like you can't really, without any particular question, you can't really go into too many, just like applications of it. But say we have some matrix. Let's call it 1, 0, 0, 0, 1, 0, 0, 0, 1, and then like 4, 8, 10. Okay, this is onto because there's a that's what I was forgetting to write. That's how you find it. Those are your two big, like how we determine if it's onto or one-to-one in like a mathematical, like seeing the numbers context.
Can you zoom out a little? It's kind of zoomed in weird.
Yeah, it's kind of hard for me to write because it's only as big as my iPad, so I can't write particularly small.
It's all right. Thanks.
No, you're totally okay. Like, yeah, you're good, but I'm not fantastic at writing small. So I'll do my best. If you can't see anything, this is going to be recorded. It'll be posted. You can go back and see it, or you can ask in the chat. So here, this is onto because you can tell we have 1, 2, 3 linearly independent vectors, which is our number of rows. Okay, so this, so for this one, like the domain is our dimension of x. It's our number of columns. Okay, R4, codomain. This is our number of rows. Okay, domain is number of columns, codomain is number of rows. And your range is how many independent vectors you have. So in this case, we also have our 3. Okay, these two are the same. That's the big like application. We can get every b, but because we have a dependent vector at the end, like we have a not pivot column, we can have multiple ways to get there. We have a free variable. We can adjust things so that we can get to 0, 0 in a non-trivial way. These are all like equivalent statements. So this, yeah. Well, not just, but that's like if it is onto, then, well, don't think about the zero way, but in this particular case, because this row doesn't have to be here, but since it is, like it's not 1-to-1, but it is onto.
Oh,
Okay.
sorry. So if that row was 0, 0, 0,
Yep,
like then would it still be on two?
it would.
And
Or if
then
that
like
last
let's just
column
say
would be, yeah.
okay.
Yeah.
Does
Wait, could you repeat that? If the last row is wait, is
Column.
it the last? Okay, so the last column, because I was gonna say onto
Yeah,
means
yeah,
that.
that's backwards, because then you wouldn't have a pivot in
Okay.
every row.
Yeah. All
Sorry, yeah,
right.
it's the
No,
last
you're good,
column.
you're good.
does
This
domain just mean number of variables?
Say that again?
Does domain just mean number of variables, like it's an
Yeah,
R
your number of columns, because if you'll, like the first part of, like, remember when you had just equations, this is like,
Yeah.
oh, shit, that's a race. It was like X, Y, Z, and we'll call it like alpha or something, right? We had 4 variables, we had 4 columns. That's where we start. We start in 4 dimensions with 4 different unknowns.
Thank you.
So that's how we get our domain, and our codomain is whatever it spits out. So in this case, we're getting like, we'll call it, oh God, I don't know, an A, B, and C vector, right? Because that's what our B is. B is in the span of the columns of A. That's the whole point of linear algebra. Can you guys see what I'm writing? Someone just said that in the chat.
Oh,
So
I
our
don't know what
codomain is where our B lives. Our range is where our B can be. So that's like our span. Creates the range, if that makes sense. So our number of pivot columns creates the range.
What's the relation between the codomain and range for one-to-one functions? Is
For
there
1-to-1, they're
or-
equal.
yeah, for one-to-one.
Yeah, the whole point of onto is that our range equals our codomain.
And what about for one-to-one?
For 1-to-1, that's not necessarily true, because we could have like a tall matrix, right? We could have something that looks, well, I guess I should keep those there. We have something that looks like 1, 0, 0, 0, 1, 0, right? We have 2 linearly independent vectors. We have a pivot in each column, but not in every row. So like we can't get the B like 0, 0, 1, right? Like there's no input X, Y to get us to this B. But there's no solution. But for every B, there is either a solution or not a solution for 1-to-1. There's no like, there's different ways to get there. There's no like there's no 2 or multiple ways to get to a vector. For every B has a unique input. Okay, or it doesn't have an input.
So for that matrix, the codomain would be R3, but the range would be the XY plane.
Yeah, you don't need to specify as specific as that. You'll just call it like, remember when we were doing like the stuff earlier, and this would form an R2 and R3. Oh shit. This forms our range and our codomain.
Would R2 be if the answer to all let me think. If we got an answer like we got a plane where Z always equaled 1, would the range still be R2 in that case?
We can't do that in matrices.
Hmm.
The range it would depend on the other stuff, because like if we have Z equals to 1, then we have like a set B, right? You don't need to think about that too hard. That's not anything that you guys like need to know. But the like purpose of what we're doing right now, we're not thinking in terms of sets or like subsets or anything like that right now. That's the condition that we have to include the 0 vector, right? It doesn't satisfy that, so we can't even think about 1-to-1 or onto. But yes, if you were to set Z equals to 0, Z equals to 1, you would still have an R2 and R3. That's how you could think about that. Okay. Questions about this stuff generally? Again, we're going to get into questions pretty soon, but just this is basic
I
concept.
know you explained it earlier, but I was just gonna say, could you re-explain what you said for the dimension versus the column space?
Dimension versus column space? Yeah. Dimension is the dimension of the overall like matrix, or the dimension of the column space?
Dimension of the column space versus just saying the column space.
Yeah, dimension of the column space would be this number here. The column space would be like span vector vector. Okay. That's the 2 that I squared. That's our dimension of our column space. But our column of A is equal to like that. Okay. That they're just like they're describing the same thing but in a different context. Okay. Okay, so that's 1 onto column space, null space, and now let's just talk about like just a quick like how to do matrix multiplication. So one of the things you guys learned in the worksheet, it is not unique. What that means is like if CB is equal to CA, that does not mean B is equal to A. Just like an idea, like that's matrix multiplication is not unique in the way that like CX equals CY, and just like general algebra terms, this means X is equal to Y. Okay, this is in algebra. This is in matrix multiplication. Okay, that's just a statement. We did work through that on one of the worksheets. We talked about it on one of the worksheets. So how do we do it? We have 2 matrices. Okay. We'll call this 3, and we'll call it a 4 by 4. 4 by 4 times 4 by 2. Okay. Well, we'll make it a 4 by 3 just so you can see it a little better. That's really 3. 4 by 3. Okay. Let's fill this with some numbers. 1, 2, 0, 0, 4, 0. 1, -1, -3, -2. This is just arbitrary. This isn't anything like significant. Oh, I'm missing a.
That's 4 by 3.
Yeah, I know. I saw it. Well, we'll just add. Oh, come on. There. Okay, and we'll call this 1, 0, 0, 1. 1, 1, 1, 1, and 0, 0, 0, 1. Okay, how do we multiply this? So the first check we have to have is we write out the dimensions next to each other here, right? And they have to have the same inside term. If they do, fantastic, we can multiply. If they don't, you can't. Okay. So whatever these 2 numbers on the outside are, this outside 4 and this outside 3, that's what your product's dimension is going to be. All right. So how do we matrix multiply in practice? The way I like to do it, I rewrite it in a form like this, where A, B, A, and B. This isn't anything that you might have learned. I talked about this last time kind of briefly. This is me just showing how I do matrix multiplication in a more simple way. You can think of it as every row times every column gives you your product, but to actually see it as you're doing it, I feel like this way helps a little bit. So I'm just going to write this nice little grid. Okay. It's okay if this doesn't make sense yet. Okay, so how do we do this? So we're looking first for this entry here. Okay, so how do we find it? I'll build my little bridges. And what this means, this first one is 1 times 1 plus 0 times 0 plus 2 times 0 plus 0 times 1. Okay, and that's what this entry here is. Because it's the column and the row that line up to that entry. That's what this grid is supposed to help show you guys. So this is just 1. I'm not going to go through all the arithmetic of this, but for example, if I wanted to find, like, I don't know, this one here, right? This entry, I would take this row and this column and multiply each of the entries together. So it would be 0 plus 0 plus 0 plus 1. What does that give us? Obviously, that gives us 1. Okay? And you just fill out your matrix like that according to the multiplication. Okay? Any questions on how to multiply just like at a base level? Cool. All right, let's move to some questions. What are you guys struggling with particularly?
I have a quick question.
Yeah.
So, can you talk about for a second subspaces and specifically their relationship with bases?
Okay. Is there any like question that sparked this in particular, or is it just like a general like?
It was just like a general question that I had.
Okay. So subspaces. That is not a beat. Subspaces. You have 3 conditions. Okay. What are they? Hopefully you should know them by now, but that's okay if not. Contain 0 vector. Okay. You plug in 0, you get 0 out. If it does, check. Doesn't mean you have a subspace, but it's the first check. 2, closed under multiplication. Oh, no, addition. Addition first. Technically, you can go in either order, but close under addition. So if we have u and v, which are both in our like subspace, does u plus v still exist in that subspace? That's what that means. Okay, and for the third condition is closed under. What is that? Under scalar multiplication. Okay, so this is if v is in our subspace, is c times v in our subspace. Okay, those are the conditions for subspaces. A basis it follows these same conditions. Basis, it just creates a space with a set of vectors traditionally. So like in like a traditional column space question, it would say something along the lines of find the columns that form a basis for the column space. Okay. So what that means is you're getting linearly independent vectors, and you're just kind of like those vectors are your basis. So your basis is just a set of linearly independent vectors that compose your range. Okay, for any particular matrix or any kind of transformation like that. Does that make sense? Bases also
Yes.
it's just like a different context that we're talking
Could you
about.
repeat that again?
Yeah, which part?
About bases.
Yeah. So with bases, the idea is like vectors form a basis is traditionally how it's written. So if vectors form a basis, there's no redundancy. So God help if that's spelled incorrectly. No redundancy. That means there's no like dependent like vectors. Like we can't say that 1, 1, 1, and then also like 1, 1, 0, and 0, 0, 1 form a basis. These things do not form a basis because this is redundant. Okay, these two do though. They form a basis. They all form a column space, but this is just our like base level what we need. Okay. Cool. These will also satisfy the condition. Like your column space, your spans, those are all technically subspaces. Your range is a subspace of your codomain. Okay. And the dimension of that depends on how many vectors you have. Okay. Cool. Been about half an hour. I think we should try to move into questions now. Okay, so what did you guys find particularly confusing?
Yeah, could you explain the question 9 of the sample test 2B?
Sample test 2B. 9 and 2B. Okay, I'll do this and then I'll take the chat. Yeah, make my way there first. Sample midterm 2B. You said question 9?
Yeah.
Okay. So, question about the definition of one-to-one. So, 2 parts. A, T goes from Rn to M. The statement is if n is less than m, t is not 1 to 1. Okay. So if it's n to m, okay, that means we go from means we go from columns to rows. Okay. If n is less than m, so that means we have a tall matrix. So this is not drawn right. So something like this, right? Oh, I got that backwards. Is never 1 to 1.
That's correct, John.
Huh?
The drawing seems correct now.
Okay, cool. So it is not 1. So this is the statement we're saying, is this true or false? Okay. If we have a tall matrix, can we have a pivot in every column? Yeah, right? Because we're not like, there's not so many rows that like we can't fill all of them. Like we can have like a 1, 1, 1 and like 20 or 30 entries under them, right?
The answer is false to this question.
It is false. That means if
yeah.
this part is false, so it can be 1 to 1. It's confusingly worded. You're just saying if that statement is true or false. In this case, it's not, because it could be 1 to 1. Okay. For part B, going 3 to 3, R3 to R3. So that means our A is some 3 by 3 matrix. So it's a projection onto the YZ plane. So if we're projecting onto our YZ plane, you could solve this question in 2 ways. You could get the matrix when you're going from an X, Y, Z to going to a 0, Y, Z. So in this kind of matrix multiplication, you can think of like your entries going across is how many times each variable is present. So like for this one in particular, like this top, like here going into 0, we have 0x is present, 0y present, and 0z present. Okay. For the second row, we have 0x, 1y, and 0z. For this bottom one, 0x, 0y, and 1z. So that's our matrix A. Another way you could think about it is you're projecting. So you're creating an R2 and R3, so your range and your codomain are not the same, so it's not on 2. Okay. Questions from the chat. How to find out if matrix, that's important. How to go over if something is closed under addition. So we'll just talk about this because I know this is like some subspace stuff. Let me find one from... Yeah, so let's say I give you the subspace X, Y, Z is in R3, given X times Y greater than or equal to 0, is this subspace is this A subspace, okay? Check 1. If we plug in 0, do we get 0? If we plug in 0, 0, 0, that means we have 0x times 0y, that is greater than or equal to 0. Check. So contains 0. Okay, that's condition 1. Condition 2, close under addition. How do we check this? So it can be a little tricky when thinking about like cases and stuff like this. So let's say we have a U, that's a U and a U and a V. Okay, both satisfy our conditions, right? So let's say U is equal to U1, U2, U3. Okay, these are just our XYZ for this particular U that satisfies these conditions. Okay. V equals V1, V2, and V3. Okay. Right. So, something you'll note is our third entry doesn't matter at all, right? It isn't part of our like conditions, so we kind of can just ignore it. So we're trying to see if U plus V is in our space. Okay, so u plus v, we add them component-wise. So u1 plus v1, u2 plus v2, and then u3 plus v3. Okay. What we're trying to see is now, after we've added, does u1 plus v1 times u2 plus v2, is this greater than or equal to 0? Okay. I like to think of this in terms of like 3 particular cases, right? So in the case that so when 2 things multiply together to be positive, that means both of them can be positive or both of them can be negative. Or particularly, they cannot, like one can't be positive and the other negative, right? Okay. So let's say that they're both positive. So we'll note that here we have positive plus positive times positive plus positive. So this is plus times plus. So this that's true. Okay, but you have to check all of your conditions. This is one of the more tricky examples, kind of like algebraically. But in the other case where we're adding negatives, it's the same idea. Negative plus negative is still negative. Negative plus negative is still negative. Okay. But in the case that where it's a positive and a negative plus a positive and a negative, do we know if they're both going to be positive or they're both going to be negative? We don't. So to like check, you could multiply this out and like solve and like do all kinds of like fun algebra, crazy stuff that I don't even want to like consider. But that's like beyond the scope of this class. Like that, you're not expected to be able to do that sort of stuff. But like one example would be, say we have like u equals -3, -1, 0, okay, and v equals 2, 2, 0, okay. Is it true that u satisfies our conditions? Yeah. -3 times -1 is +3. Is it true that v is in our space? 2 times 2 is 4. Positive. Fantastic. But u plus v is -1, +1, 0. -1 times +1 is definitely not above 0. So this is not closed under addition in this case. So like the idea with general like closed under addition, define a general u, define a general v, see if when you add them together and apply your conditions, if it's still in the space. Okay. Multiplication stuff can get a little tricky. Absolute value, like all of these are just different cases that you guys have seen. Doesn't mean that you like just know them off the top of your head. Definitely don't. All right. Are there any recurring?
A quick question about closed under addition. Would you have to be adding constant or just if it was?
Sorry, I'm not sure if it's just me, but your mic is kind of like buzzing.
If it was something random to test for
Okay.
that as well.
Your mic isn't making a great. I can't hear you very well, so if you could send your message in the chat. Okay. So I'll just pick one of the. If anybody's seeing like a recurring question come up in the chat, like let me know, say something, and I'll make my way to there. So I see on the first practice.
I have a question about being closed under scalar multiplication.
Yeah.
So if there's an like for example, one of the questions on the first practice exam was like let the subspace V be x, y, and R2 where x times y is greater than or equal to 0. But if the scalar c is negative, would that just make it?
Tricky algebra question. Okay, so the question states, like, say we have an xy in R2. Obviously, it's an ordered pair. Given that xy is greater than or equal to 0, right? We're asking if it's closed under multiplication. So let's give our u, okay? U equals u1, u2, such that this is true, okay? So now does cu, is this still in the space? So cu, we multiply component-wise. Okay, so applying this condition to this, we get cu1 times cu2, and we're asking, is this greater than or equal to 0? Okay, so we multiply this out, and this gets us c squared u1, u2, greater than or equal to 0. Okay, c squared, regardless if it's positive, negative, or 0, it's either going to be positive or 0, which satisfies this condition. And then we know also that u1 and u2 satisfy this condition, because that's what we started with. Okay, does that answer your question?
Yes, so it is closed under scalar multiplication.
So it is, yes.
So like, what if U1 was positive and U2 was like negative? Then
If u1 was positive and u2 is negative, then this does not satisfy our conditions, and we don't even need to consider it. That's what, like, when I define like a general u, that's a u that satisfies the conditions. Okay. Yeah, so that's like the whole like idea behind why we're able to do this.
so if like the question were to ask like if this is like a subspace, it would be no, because like there is a possibility for it to be like negative.
This is, so if C was like, this is closed under multiplication. Check. Okay, that's what we just proved. Does it contain 0? When you plug in 0, 0, it's still greater than or equal to 0? Yes, but it's not closed under addition. It's the same process of like this last set I just did here. Since it's not closed under addition, it is not a subspace.
I had a question. I don't know if you have the plus practice to
plus,
but I can read the question, and I think
okay.
Wait, so my question is like it was about so it says like the transformation R2 to R2 is defined as follows. First, it flips the plane over the x-axis.
Mm-hmm.
Then it rotates the plane counterclockwise by 45 degrees. And then it stretches the x direction by a factor of 2. So the way I thought you approached this was like multiply the different transformations.
It is.
But I'm not, is like, what's the order? That's where I...
Fantastic question. So think of it as we start with our big transformation matrix A times our x, right? So this, we can break it up into like each of these individual, like say A is like our final product, right? So what we're doing is A times our first one, times that, times our second one, times that, times our third one. Okay? So left, right. Like first, last. Okay? Yeah, think about it chronologically. We start here, then we do this, then we do this. Okay, those are bad arrows, but whatever. Okay. So I see question 12 on practice midterm B. So let's see what that one is.
So first would be like the projection.
Yeah. Well, first it says first we flip, and then yeah. I might have written that down wrong. And then we rotate, and then you stretch. Okay.
Okay.
Does that make sense?
Could you show like so? What would?
Yeah. So for like, flip over x, 1, 0, 0, negative 1. Rotate counterclockwise 45 degrees. That's 2 over 2, negative root 2 over 2, root 2 over 2, root 2 over 2, and scale x by 2, 2, 0, 0, 1. Okay? Multiply these together, you'll get your answer.
From right to left?
Yeah. Well, from left, it doesn't matter, but you just have to have them paired correctly.
Oh, okay.
Because, like, if we did this backwards, like 1, 0, 0, negative 1 times this stuff I'm not going to write again, times 2, 0, 0, 1, these are not, let's call that like an ugly equal sign, not equal. Okay? Yeah, so that's just, it's just the ordering of it.
Gotcha.
All right, so question 12 is actually very similar to this one. Linear transformation, first projection on the x, and then rotates 90 degrees clockwise. So if we project onto the x-axis, what does that mean? It means we're going from an xy, so this is where we start, and we're ending in an x0. This is where we end. Okay? How do we determine how we do that? With a matrix. So the way I like to think about it is we go by row and we count which of our variables is present. So how many x's are present? Because this is x and y. 1 x present, 0 y present, and then 0 x present, 0 y present for the bottom. And then rotating 90 degrees counterclockwise. Just the thing to know, your rotation matrix, cosine of theta, negative sine of theta, sine of theta, cosine of theta. However, the important thing to remember is that this is pre-calc, like angle stuff. So we measure our angle going this way as a unit circle, right? So counterclockwise is positive, clockwise is negative. Okay? Counterclockwise positive, clockwise negative. Okay? Like this matrix is just something you need to know. Just for like the sake of this, like it's not, I don't really love telling students to just memorize things, but this is something that you just need to remember. Do you think you should relearn the unit circle? I don't want to tell you need to relearn the unit circle, but it's important to know like your pi over 6s and pi over 4s all the way around the circle. So which did you say was positive? It's just a positive angle. Like these, like this matrix never changes. Your theta changes. Yeah. This top right sign is the one that's negative.
This is the one for counterclockwise, right?
Clockwise or counterclockwise?
This is the matrix for both.
Okay.
Okay. But counterclockwise means you have a positive theta.
Yeah.
Counterclockwise means you have, or clockwise means you have a negative theta. Okay.
Oh, gotcha.
So plug in a negative angle here if it's clockwise. Okay. Technically, like if you plug in a negative angle, you'll get cosine of negative theta, sine of negative theta, negative sine of negative theta, cosine of negative theta.
I'm
Okay,
pretty
this
sure
is if you're
that's
plugging in a negative angle.
I'm pretty sure that still comes down to like cosine theta, sine theta, and
does.
then negative. Yeah.
Yeah,
So
so
you could
one of the
just flip that
definitions of like cosine x is equal to cosine of negative x, and negative sine of x is equal to sine of negative x. Okay, so this is just cosine theta, negative sine theta, sine theta. Okay, but I like to stick just with this here and just determine if my angle is positive or negative, so I don't have to try to remember two matrices and confuse myself and all kinds of stuff like this. So my word of wisdom would be this. That rotation counterclockwise is positive, clockwise is negative. Okay, and going back to the question we were just at, so our rotation matrix, given this, it was what, a clockwise, 90 degrees counterclockwise, so cosine is 0, sine is positive 1. Okay, how do we determine our A? We multiply our matrices together in reverse order, 1, 0, 0, 1. So what is the product of this? 0, 1. Nope, 2 by 2. So this gives us 0, 1, 0, 0. Okay, that's our ABCD, I believe. And it is. Unless I wrote that wrong. I think I wrote that wrong. No, we're good. We're good. Sorry. Okay, next question. I see number 5 on 2B. Number 5 is... Okay, so we're going from R2 to R3. Okay, and we're given the transformation is equal to 2x. This is, I guess, whatever. x1 minus plus 2x2 minus x1. Oh, there's a comma there. Minus x1 plus 3x2, x1 plus x2. Okay. Which of the following describes all x so that tx equals 0. So from this, I would make my matrix. Okay. So we're going from 2 to 3. We're going from our x being 2 to our b being 3. And we're resulting in 2x1 plus 2x2, negative x1 plus 3x2, x1 plus x2. Okay, So how do we find this? So how many x1s are present in this? 2. How many x2s are present? 2. And going down rows here, -1 x1 is present and 3 x2 is present. Because the idea is, remember, x1, x2 here, we multiply 2 times x2, or 2 times x1 plus 2 times x2 gives us this, okay? And then going down a row, -1 x1 plus 3 times x2 gives us that. And then finishing at the bottom, 1 x1 plus 1 x2. Okay, this is our matrix. This row reduces, I believe it's 1, 0, 0, 0, 1, 0. So what does that mean? It means our column space has a dimension of 2. It means our column space is a plane that's composed of these two vectors. So for this question, it asks us, which of the following describes all x so that tx equals 0? Okay, so we're describing our x to get us tx equals 0. If the columns were dependent, right? Basically, this is like asking us, what is the dimension of our null space? It's 0. And if our dimension is 0, then our 0 is just a point. Okay. So this is asking the dimension of our null space. And since we have pivot, we have no free variables. And we have no free variables means we have no null space. Okay. Because in parametric form, there wouldn't be anything to form. So describing the range of t, okay? So here we found that we have 2 pivots, which means we have 2 linearly independent vectors that form a basis for the range. A lot of new terms for this stuff, this unit, but 2 linearly independent vectors form column space. Means dimension of column of A is equal to 2, which means our range is in R2, and we have 3 rows, right? So we have 1, 2, 3 entries for each of our 2 vectors, so it's in R3. Okay, so this describes a plane in R3. Cool.
I know this goes back to like the last test, but
That's
just
okay.
like a quick thing. Is it a plane because there's 2 pivot points? Because there's no free variables. Okay.
Very good.
I just want to make sure.
Yep. We could have a different. The free variables doesn't tell us anything. The free variables don't tell us anything about our range. Because like say if like we reduce this to get something that look like this, like ignoring this up here for right now. Here, this all would still be true. Okay, but this would also mean null space of A equals 1. Okay, so everything else is still true. We still have 2 vectors that create in R3. Well, two vectors that create in R2 in R3. Okay.
Would the null space be a line? Or
the null space in this case would be a line, right? Because if dimension of our null space is 1, that means it formed in R1, which is a line. Right? Cool. That's the whole like idea behind like dimension of column space. It means like our columns form whatever that R to the whatever that dimension is. So in this case it's an R2, so it forms a plane. And in this case our null whatever our null space is, our dimension of our null space gives us our like dimension of our null space gives us like the dimension of that like span. So in this case it's an R1. Okay. Sorry these terms are so confusing. Hopefully they're making more sense to you by now. And yes, in this case R3 is our codomain, R2 is our range.
So for the first part of this
row of yours at the
question,
bottom contribute?
No. Go ahead.
Oh, okay. So for the part A of this question that we just did, we said it was a point in R2, but why is it R2 and not R3?
because our null space, right? We're talking about describes all x, okay? And our x is talking about this boy here, right? Okay, and this is only in R2.
I see.
Okay, does that make sense? Our solution, or our null space exists because we're talking about x, okay? Our column space exists in this dimension because we're talking about our b.
So it's a point because both of the variables have a pivot in the column, in their columns.
Yeah.
And
so the only solution is a trivial solution, which is 0, 0. And then you're done. You could also technically find that given like dim column A plus dim null A. In this case, it equals 2 because we had 2 columns. So we found our dimension of our column space to be 2 plus dimension of our null. So that means this has to be equal to 0, right? So we have no null space. That's what the first question is asking, is it's asking the dimension of our null space. Okay. All right. Another question. I see a lot of questions being asked and answered in there. Just, sorry, go ahead.
Oh, I think it's lagging for me. I'm sorry for interrupting.
Oh, no, you're okay.
Okay, but could you explain number 6 and 2a?
6 and 2a. On it. Use 2a. If you guys are able to walk yourself through the midterm, answer it. However, it doesn't really matter how you answered the first time. But then if you look back at it and you understand how you did things wrong, you should be pretty set for this midterm. So did you say question 4? Sorry.
Oh, sorry.
Which question? 6?
Number 6 and 2a.
Number 6, right?
Yes.
Okay. All right. So this question states, suppose a 3 by 7 has rank 3. So just from right here, what does this mean? Okay, we have a rank of 3, which means dimension column space A equals 3, which means we have 3 pivots. And if we have 3 pivots, how many not pivots do we have? We have 4 not pivots. Okay, or free variables. Right, same thing.
Good question.
7.
3. This is not related. I mean, it's related to this question, but like, but it's not the exact like. Would the column span of this be 7? R7?
The column.
I mean, it would be R cubed. Yeah, it would be R7, right?
The column space?
Yeah.
No, it'd be R3.
Oh, okay. So column space is based on number of rows?
Column space it exists in our number of rows. It's column space is like our linearly independent columns. Give us column space.
Oh, I see.
Okay,
and that was just being the number of rows generally, because you can't have.
Be very careful saying generally.
Okay.
It should be the number of pivots, because you can have like something with like a lot of rows, but if it doesn't have like enough pivots, right, that determines like, so the column space or the dimension of the column space is always going to be equal to the rank, I'm pretty sure.
Yeah, that's the definition of rank. It's just a term to cut out dimension column. You just say rank instead.
Wait, I didn't quite understand that. Could you explain again?
Yeah, rank, like the definition, it's just shorthand. These mean the same thing. Like that's exactly what rank means. So dimension of column space is your number. It is the same thing as your number of pivots. Okay, and like say we had like instead if we had a 4 by 7. Okay, with 3 pivots. Okay,
got it.
We have 3 pivots, so that tells us our range is going to be R3 because it's R to the number of pivots. In R to the number of rows, R4. So we do not have a pivot in every row or every column, but this will yield the column space will be this. Okay, some kind of R3 and R4.
So just to summarize what you're saying, it's basically R to the number of pivot columns in R number of rows.
Correct. Yeah,
Got
your
it.
range and your codomain.
Got it. Cool.
Yep.
I'm just
They weren't really confusing, and they give you these big general ideas on how to find like range and codomain. It's just kind of unnecessary, but
you could also like just see it. So like if you have 3 pivots and you have 4 rows, that's basically just saying like you have a plane in R4, which is the column space.
If you have 3 pivots in R4, then you have 3 space, but it just doesn't create the whole thing. Okay, so going back to the question, you guys continue. You go ahead.
Can you repeat what you just said one last time about what he just said about the space thing?
Yeah, so the whole like idea with like this whole rank dimension, like rank is equal to your dimension, your column space is your number of pivots. Your number of pivots gives you like your R3. It gives you the dimension of your range, okay? In R to the rows. Okay? This is always true. This is always your range in your codomain. Okay? That's how you find them. Your codomain is your number of rows. Your range is your number of pivots.
Okay, thank you.
Absolutely. All right.
Wait, and so column space was what again?
Column space is equal to like the span of your columns of A. So like whatever the dimension of your column space is, that's your range.
Okay.
Sorry. If you guys have more like individual questions or anything, email me. My office hours are also tomorrow, 2 to 4. Skyle's 2:30. This is on the Canvas page, but I'm going to keep going for a little bit longer. Okay, so for this question, if a vector b is in the codomain, what must be true about the matrix equation ax equals b? So this right here, like we just talked about, having 3 pivots means like the column space gives us this, R3 in R3, right? So it spans all of R3, okay? So if our codomain equals our range, this means something is what? Onto. Okay? When something is onto, that means there is at least one way to get to every b. Okay? So if there's at least one way, you either have one solution for everything or multiple solutions for everything. But in this particular case, we have 4 free variables, right? Because dimension of column space, A, plus dim null of A equals number of columns. So 3 plus this equals 7. So your dimension of your null space is that. That's how you can tell that you have 4 free variables. Okay, your dimension of your null space is always equal to the dimension of the number of free variables you have. Okay, because just think back to parametric form, right? You have a vector for each free variable. So if it's onto, that's the like everything has at least one solution. In this case, we have 4 free variables, so there's infinitely many ways to get to all of them. Okay, this is a combination of having like your this be true and having free variables. Okay, if this was like if instead it told you like it had a rank of 2, okay, you'd have this would no longer be true. This codomain is not equal to your range. But if it said you had a rank of 3, which must be true, can't really determine if it has a solution or not. Because there will be some B's that don't have a solution, but those who do will have multiple solutions, or at least one way to get there. Kind of confusing. They probably won't ask you anything so specific. So, okay. Let's see, questions in the chat. I guess I'll just.
I have a quick question, real quick.
Mm-hmm.
Could you go over question 19 on practice midterm 1? I just I've never seen column. Yeah, on the first midterm review, question 19, like 2A.
Okay, so 2A. Okay, cool. Because we also had a very similar question in the last one. So this fun thing is supposed to make a little more sense, but does it? Who knows? Let's make it make sense. Okay. So we have column space of A. 1, 2. That crosses 0. And the null of A. 2, 1. You guys should probably expect a question like this. Not that I don't know what's on the midterm. I don't have access to viewing it, but this kind of question really shows if you know what column space and null space mean. Okay, so we have column space and we have null space. Okay, so our column space is equal to what? It's equal to the span of the vector 1, 2, right? Because it's just a line. It's the span of that vector. You can pick like 1/2 1 or -1, -2. It doesn't matter. They all create the same thing because it's just on a line. Null space equals the span 1. Okay, so if this is our column space, well, first of all, we know each of these have 2 variables. Essentially, well, we know since column space. Okay, so column space is dimension 2, so this is 2. Well, not the vectors in the column space have a dimension of 2. Sorry, the vectors in the null space have a dimension of 2 as well, so that means we have 2 columns. Okay, so what do we know? We know column space, so all of our vectors have to have some kind of form, like 1, 2, and then 6, 12, or something that like both columns satisfy this, right? They're not linearly independent. Okay. Does that make sense so far? Hopefully so. So we'll just name our first column 1, 2, because everything else we can just base off of that, okay? So again, I got this right from our column space. Dropped it right in there. That's what our first vector is. Okay, null space. Span of 2, 1. So what does this mean? It means we have x1, x2. So we're converting this back to parametric form equals some number t times 2, 1. Okay.
And 0.51.
Huh?
Would 0.51 be an option for the second column?
I'm not quite there yet, but we will see. You can't, it's not as intuitive to just like, oh, the second one is 2x1 equals 1x2. You can't just snap like that because this tells us parametric form, and there's some like negative stuff that we're going to see in a second. Okay, so you will see it like right here actually. So this has x1 equals t2, t times 2, and x2 equals t. So we can just call t is equal to x2, or because we know it's going to be a free variable in front, x1 is never free in our particular case, so we're just going to call it x2. Okay, that's a long-winded way to say like, hey, this has a 1, and the first one can't be, like, we can't lead with the next one, so x2 is out front. Okay, so this gives us x1, x2 equals 2x2, x2. Okay, so this gives us the equations x1 equals 2x2 and x2 equals x2. So that just means it's free, okay? So what this tells us here, well, let's rearrange this. x1 minus 2x2 equals 0, and we're going to subtract this over as well. 0 equals 0, okay? This is our reduced row echelon form. Okay, so from this matrix, we have 1x1, negative 2x2, 0, and 0. And because remember, null space, we augment with 0. That's like you can ignore this. This is the important thing you need. Okay. So like essentially, like you're taking this and you're slapping a matrix over these. Okay. So this is what your reduced row echelon form looks like. Okay? So for a reduced row echelon form to have like 1, -2, 0, 0, right? Just taking the coefficients from that. We can see that whatever the first one is, we multiply it by -2, so 1, -2. And for the second one, does it make sense how we go, like, from just for the first row at least, right? Like, if instead this was like, 0.5, this would now be -1, okay? So we have 1 here. So we need to satisfy this here, okay? That they have that form. So 1, -2. Now we have 2. What's 2 times -2 to get from here to here? -4. There's your matrix. Any questions on this? I do expect there to be questions. I know it's really confusing.
Could you explain that last step of when you got 4?
Mm-hmm. Absolutely. Okay, so having this, like, do you understand how I got to this reduced row echelon form, like, idea here?
Yes.
Okay, so if this goes into reduced row echelon form like this, it means our, like, second row is a multiple of this as well, right? Because it cancels out. Okay. So essentially what this means is all of our rows have this form, okay? So if they have this form, 1, -2, if like the first one is 2, then the second one is -4. If the first one is pi, the second one is -2 pi. If the first one is 10, the second one is 20. Okay? These are just all different examples of like what you could pick, because technically we didn't have to pick 1, 2. Like we could have picked 0.5, 1. Okay? So if I picked, that's why this question isn't like input answer yes or no, because there's an infinite way to do it, infinite amount of ways to do it. 0.5, 1. So applying this same condition that we had, this becomes -1, this becomes -2. Okay? And you can double check to make sure that our span of our columns is still, like each of these columns is is like a linear combination of whatever these are, but in this case it's just 1, so a scalar multiple of it.
Wait, so you got, so I get that x2 is equal, the x1 x2 is equal to x2 times 2 1, but how'd you get x1, and then you got x1 is equal to 2x2, but then how'd you get x1 minus 2x2 is equal to 0?
So do you understand how I got the parametric form here?
Yeah.
Okay. Do you understand how I got to here?
Yes.
And then my equations from that, I just subtract them over to set them equal to 0.
Wait.
Right?
1 is equal to 2x2. And then you want all that to be equal to 0, right?
Mm-hmm. So you just take this and you subtract it over. And then from here, that's when we pull our matrix.
Oh, okay, I see.
Mm-hmm.
I see.
Cool.
Because x1 minus 2x2 is equal to 0, and x2 minus x2 is also equal to 0. x2 minus x2 is 0, so 0 is equal to 0, and x1 minus 2x2 is equal to 0.
Yes.
Got it. Thank you.
You don't need to understand every statement he just made, by the way. That's okay. All of these will make different amounts of sense to different people.
I mean, I would prefer to, so I know the content better, but.
Okay. Well, I mean, whatever makes sense to you as an individual. But any more questions? I'll probably take 1 or 2 more, and I'll call it a night.
What are the differences between a linear and a matrix transformation?
All matrices are linear. Not
okay, so they're the same thing. No, okay.
All matrices are linear transformations. Not all linear transformations are matrices.
Okay.
Okay.
Could you give an example?
They're just kind of like different, and you can like, is this linear transformation a subspace? So given the linear transformation R2 to R4, you can think of that as a matrix as well.
So is that why you have to verify like that a linear transformation is linear but not with a matrix transformation?
Is linear but not with a matrix transformation.
Like you have to go through like the conditions?
Yeah. So like the technical way to like say it in like perfect definition, all linear transformations can be described by a matrix transformation. Also, every matrix transformation is a linear transformation, okay? So every linear thing we have, we can describe it with a matrix. And for like, it gives us like T from R4 to R6. We choose to describe that as a matrix, okay? You could describe it as a set of equations as well. But if you remember like the very first week, we showed that a system of equations can be described in a matrix. Does that answer your question, I hope?
Okay, so they're different things, but a linear transformation can still be described as a matrix, and a matrix transformation is linear.
Correct. Yeah, that's exactly right.
Okay, thank you.
All right, I see someone begging for 2B number 6, so let me do that one really quick. Quizzes. Sorry if I look past any of y'all's questions in the chat. There's only so much I can do for 100 people at one given time.
How can we access the recording afterwards?
I'll just send an announcement.
Okay, thank you.
Yeah. Question 6. Okay.
They said they meant to say number 4, not 6.
Meant to say number 4. Word, heard, done. Okay. Alrighty. So, 4. Thank you for letting me know, by the way. Because I have my Blue Jeans open in one window, and then I just scroll to my Safari in the other. So I just kind of go back and forth, and I can't see chat while I'm doing that. So just interrupt me like you did. Okay. That's not to say interrupting is bad. 1, 1, 0, negative 2, 0, okay. 0, 1, 2. Find A such that null of A equal to just 0. Okay, so we don't have a null space. Dimension of a null space is 0. We don't have any free variables. Okay, if we don't have any free variables, that means that this is a linearly independent vector. So essentially, our goal is that RF of A is equal to 1, 1, 1, 0, 0, 0, 0, 0, 0. Okay. Which is the same thing as saying 1, 1, 0. Well, we're trying to say that negative 2, 0, and k not linear combination of 1, 1, 0 and 0, 1, 2. The easiest way to check this is with, you could do it kind of intuitively. You could see that like, hey, this top tree is negative 2, which means we have to multiply that. We could do it that way, but I like to do it in a matrix. So we have 1, 1, 0, 0, 1, 2, and we augment it to see if 2, 0, k is in the span of it. And if it isn't, it's linearly independent. Okay. If it isn't, that means that this will be inconsistent. So our goal is to get this to be inconsistent. Okay. So let's do some row reduction. We obviously know that the first one is equal to the first like entry is equal to negative 2. So 1, 0, negative 2, 0, 1, 2. Okay. 0, 2, k. And then from here we reduce just a little bit more. 1, 0, negative 2, 2, 0. Oh, damn it. Zero. Now we're reducing that one again, and now we get k minus 4. For this to be inconsistent, this has to be non-zero. Okay. So for which value does our null space equal 0, which means the same thing as not having any free variables, which means that all of our columns are linearly independent. Okay. Or you could just skip that like middle bullshit and say null space equal to 0. It means that all of our vectors are not combinations of each other. Okay. So when is k minus 4 not equal to 0? All real numbers except for when k is equal to 4. Okay. Fantastic. Any more questions? More pressing questions? Any individual things? Any one question getting y'all kind of tripped up?
Sorry. Let me just number 18 for 2A.
2A. Okay. I'll do that, and then I'll go over one type of question which you guys have seen a couple times now, and it's just you should just know how to do it. And for like the sort of stuff, it's a common test question. So you said, what question was it? Sorry.
Number 18.
Number 18 on 2A?
Mm-hmm.
Okay. 18. Okay. So let A equals 3, 4, -1, -1. Okay. And A times A, just AB is equal to 1, 0, 1, 1. Okay. So find B is essentially what this is asking. Okay. So we have matrix A. No, shit. Remember when we have our A times B, it's A, 3, -1, 4, -1, times our B, which I'm going to raise up here. It was A, B, C, D. Okay. So let's find what this matrix is, right? This is 3A plus 4C in this entry, -A minus C. Over here, it's 3B minus 4D, or plus 4D, sorry. And it is -B minus D. Okay. Does this step make sense so far? Right? Just multiplying like a general matrix with our other 2 by 2. Yeah? Cool. I'm assuming I've heard no contradiction, so I'll assume so. So now we set this equal to 1, 1, 0, 1. Okay? So now we have 3A plus 4C equals 1. 3B plus 4D equals 1. -A minus C equals 0. And -B minus D equals 1. So we have a system of equations. As we learned at the beginning of the semester, there's a couple ways to do this. We could put in an augmented matrix, or you could do it by substitution. You could like find that, hey, A has to be equal to C. So I'm going to plug in here. Or A has to be equal to -C, sorry. -C. So then you'll find that A is equal to, this gives you -3C plus 4C equals 1. Then you find C is 1, and then you do that for the rest of the variables, just substitution, things like that. Or you could put this into a matrix. 3, 0, 4, 0, augment 1. This is definitely the long way to do it. But if this helps you, then do it. By all means, don't let anybody stop you. Okay. Row reduce it, solve for each of your variables. Okay. One last type of question is just applying the concepts of linearity. So the concepts of linearity are those few things that we talked about for subspaces. Okay. So like if they give you like t of 1, 0 is equal to, I don't know, 4, 2, okay, and t of 1, 1 is equal to, call it 0, 1, okay, and then it's find t of 0, -1. You could go backwards and you could find this matrix A given this. Why are my arrows so stupid? Given this and this. Or what you could do is you could recall that t of 0, -1 equal to 2. So 0, -1, you could test it in the matrix and find that this is a linear combination of these two. Okay, so what that means, x1 times, well, x1 times our vector 1, 0 plus x2 times our vector 1, 1. Okay. This is just saying that 0, negative 1 is equal to some number times 1, 0 plus x2 times 1, 1. And we know these numbers from this matrix, but I'm going to write it a little bit more generally just to work out the whole process. Okay. Based on linearity, it is closed under both scalar multiplication and addition. So let's split it by addition first. Plus t of x2 of 1, 1. Okay. And then if it's closed under multiplication, we can take that number out. So x1 times t of 1, 0 plus x2 of t of 1, 1. Okay. So now this we know. This we can find really easily, right? Instead of trying to just like plug and chug for that. We like having to find an A. This is all just to say that you can do it either way. This way might save you a lot of time. Especially if they give you like 3 vector, like t of 1, 1, 1 and t of like 2, 4, 8. Okay. And then from here, we found that x1 equals 1 and x2 equals negative 1. So that's 1 times t of 1, 0 was given, and that is 4, 2, plus x2, which is negative 1, times t of 1, 1, which is 0, 1, right? So this gives us 4 minus 0, 2 minus 1, 4, 1. Okay? That is what our t of 0, negative 1 is. That's just like a common like linear algebra like understanding of how this stuff works. Okay. Any last questions before I call it? All right. Thank you guys so much for coming. Best of luck on your midterm tomorrow, and email me, come to my office hours, or ask your TA. There's a lot of resources. So have a good night and good luck.
Thank you.
Yep, absolutely.
Thank you.